Okay, so in this lesson here, we're going to look at a couple more Laplace transforms, doing them by definition. And then, again, we're not going to really do these by definition uh, beyond this, but there are some, it's good to understand what the process is that we're looking at. So we're going to look at another function here, f at t, and we're going to look at e to the minus at. And then I'm going to get in the habit of writing u at t next to it. The reason I do this is because really we wanting to look at these functions for just t greater than or equal to 0. And so I'm just going to automatically put that in there to make sure that we emphasize that. Plus, the other issue is when you do an inverse Laplace transform, you automatically get a step function coming back out. Alright, so let's go ahead and look at the Laplace transform of this. So we're doing the Laplace transform of e to the minus at u at t, which is just the integral from 0 to infinity e to the minus at times u at t times e to the minus st dt. Now don't let this really intimidate you. Again, u at t is just 1, so this just becomes the integral from 0 to infinity e to the minus at times e to the minus st. And then, well, what do you do with here? You just add the exponents. So you'd have e to the minus a plus s in parentheses t dt. So I'm ready to integrate now. And when I integrate this, I get negative 1 over s plus a e to the negative a plus s times t evaluated from 0 to infinity. Negative 1 over s plus a times e to the negative infinity minus e to the 0. And again, that goes to 0, that goes to 1. So keeping track of the double negatives, we get a positive 1 over s plus a. So the Laplace transform of e to the minus at u at t is simply 1 over s plus a. Okay, so we can look at some more of these here, but this is kind of enough of doing them by hand here. There are other ones you can do here. I will write down a couple of the other Laplace transforms. For instance, let's just look at one here and then we'll talk about a table here. For instance, we could go through and do the sine of omega t, and doing the sine of omega t, there's actually a pretty slick way of doing this using complex numbers, but we won't do that. I'll just write down what we end up getting here is omega over s squared plus omega squared is a Laplace transform of sine of omega t. Now there is one other very important function to us, and this is the unit impulse function. Now the unit impulse function we write as delta at t, and the definition for this is a little strange. It's got infinite height at t equals 0, and it's 0 everywhere else. But then we also have that the integral from negative infinity to infinity of the delta function is equal to 1, which it's a bizarre function to look at, and there are ways you can there are several ways you can define this, but really the delta function the easiest way to think about this is equal to a limit of a sequence of functions. Which is weird to think about because, that's something that at this point in most of your mathematical careers you haven't necessarily thought about looking at a limit of a sequence of functions. But let's just give you an example on how we could construct this delta function relatively straightforward here. So let's look at a graph here. And there are other ways to construct it besides the way I'm doing it. I just find this way in particular to be the easiest one to see. Okay, so I'm going to have a rectangle here, and I just had this rectangle defined from negative a to a and a height of 1 over 2a. So the area of this rectangle, we don't have to do calculus, it's just, height times width. And so the width is 2a times the height is 1 over 2a, so this is 1. Now what we do is, okay, let's make a smaller. So if I make a smaller, I get minus a to a, but then I get 1 over 2a, and I know it's going to get taller because I'm going to start hitting decimal numbers, because I'm basically letting a go to 0. And if I'm hitting decimal numbers, I'm dividing by like 0.1 or 0.2, things like that, so I know I'm going to get bigger numbers. But again, here, the area is still 1. Now, basically, we look at, well, what happens as the limit as a goes to 0? Well, the area stays 1 for all those functions that you look at in that sequence. The area is always going to be 1. So if this sequence converges, the area would still be 1 because that's what it has to converge to. And then, well, basically what's happening, the function's becoming 0 everywhere except at the point x equals 0, it's getting infinite height. So this is one way to look at it. There are other ways. Now, if you talk about the Laplace transform of the delta function, that's a little bit more challenging to kind of look at and figure out, especially with the way I define the delta function. But I will just tell you here that the Laplace transform of the delta function is just 1. Alright, so that's a kind of a useful thing to have here, which is kind of why it's also called the impulse, because you just get a 1, bam, kind of thing. Now, the way we typically draw an impulse, though, if we have delta at t, since we don't have the ability, or we don't want to necessarily draw a line all the way up to infinity, what we do is we would draw a line to 1 with an arrow. But then, for instance, you might have 2 delta at t minus 1. And so if this was 1 here, and this is 2, I would just draw that for 2 delta at t minus 1. So this is how we draw the delta functions. We don't actually draw a line up to infinity. We just draw them as little impulses here. And this delta function actually becomes very important in signal processing and in discrete time instances. Alright, so let me show you a Laplace transform table. So for instance, this right here is a Laplace transform table. Now, on this side here, these are all sorts of properties that we haven't talked about yet. which we'll talk about in the upcoming videos. But over here are the Laplace transform pairs. And notice we have delta, which is 1, u at t, which is 1 over s, e to the minus at, which is 1 over s plus a. Then they have t, t to the n, t to the e minus at, so on, sine of omega t, cosine of omega t, and then they've got a phase shift, e to the minus at sine omega t, e to the minus at cosine omega t. So they have my Laplace transform pairs here. These are the most common ones that we would use. Now, I don't expect you to have these memorized. I would provide these to you on an exam, as well as these properties. So I don't expect you to have these memorized. This is from some textbook. I don't even know which one it is, but I just found it quickly with a Google search. But yeah, so these are the properties and the Laplace transforms that we would use. So while it's important to know the process for finding a Laplace transform, we are not going to actually, when doing circuit analysis, sit there and do a bunch of Laplace transforms.